Hello, Kennedy. Hello, Spencer. Hello, Adam. Nice seeing you connected. We will start in a minute. Okay, I think we will be without camera again this time. But I'm not sure if it is a big loss. Okay, so here is the list of equations we should arrive to by the end of. Oh, what does this sign of microphone unit means? Let me check that those who are on the connection here. Kennedy, Spencer, and Adam, please type or speak if you do not hear me. And if they do not hear me, they do not hear my question, right? Okay. Do you hear me? Let's wait until they answer. Or we can. Okay, very good, very good. Thank you, Spencer. So if everything goes favorably as we go through the class, we should arrive to these equations, and maybe only the first three, because this one is important, but too much for the first meeting. So if these equations seem easy, familiar, and recognizable to you, you may just disconnect or stand up and leave. If you need a few comments on them, then I invite you to stay and participate in the discussion. So first one is Euler equation, which is just basic math with complex variables. The second one is the Breuil wave, and we are approaching to the goal of, well, not approaching, but moving towards the goal of mathematically describing wavy nature of electron. And this was worth, the simple equation was worth of Nobel Prize in physics. And each person and each equation below also was of 1 million monetary prize. So those are kind of valuable. The one is Feynman will be discussion how to predict the future. Because I don't know, for me it was one of the motivation to keep going in science at the graduate stuff, because when we know that you can predict a little bit small fraction of the future, it looks cool. Okay, so after we get a little overview of what to expect, okay, so we are on number 4. It is in the blue box, and meetings were recorded in previous years. If by some reason you want to hear me once again, you can go onto this links and maybe it will be a little bit different words. So let's check if the movie will work. Maybe not, but if you run this slide on your computers that was forwarded, there is a movie when this ball, which is like a cloud of electrons, comes through double slit, and then there are interference patterns. And this JPEG is borrowed from the YouTube, so if you look for the electronic waves there, you'll see it. So last time we were discussing that what is our goal? The goal is to describe whatever happens in chemistry, reactions and characterization at quite precise method to set up fundamentals and be able to either interpret or predict properties of molecules. And in order to do it adequately, we need to go over the wavy nature of electrons and bring enough mass to do it. And we are on the path of going from simple examples to something more realistic. And one example that we just focused our attention was the vacuum tube. Another was the electron in the atom that seems to have some waves of something, and these waves want to have the integer number of nodes and volts. And it is the theory of Bohr, and we want to either repeat his path or just make it rational into this ideas. What is revolving in the atom? Why there are waves of what? And on this path, we also discussed, in fact, advanced mechanics from physics in 5 minutes with least action principle. Like same as people practice laziness, same all natural objects try to select those trajectories that take least action. And the main hypothesis that we are going to explore and push through, that the action that is getting accumulated along the path of any motion will affect how frequent this phase of this wave will go up and down. So as the action grows through the trajectory, the wave gets up and down, experiences oscillations. Make sense? And we just need to repeat this idea from analyze it from different angles with different words. And finally set up equation that we will solve for application. So on this path, we suddenly realized that dimensionality of the action and dimensionality of angular momentum, which is measure of rotation. How intensely something is rotating, how quickly angle is getting accumulated, angular momentum. So the dimensions of these two quantities, action and angular momentum, are the same. And it kind of makes a bridge between accumulating of action or angular momentum and setting that they're kind of related to something oscillating an even number of times. Okay? So the action is integral from initial time to final time of the changing. Okay, I'll design how to annotate if needed, but the action is integral of this Lagrangian, which is same as similar to total energy operator, kinetic minus potential. I'm going to integrate it over time. Okay, so we are starting the meeting number 4, and I invite those who are on the online connection to switch, well, to actively participate and ask questions, and when asking, including better do it through microphone and camera. I'll try to design a protocol to offer credits for discussion, but it is much easier, it is appreciated, it's much easier to deliver material with a live discussion rather than just mumbling to the screen. So there is so-called Planck constant, which also has the dimensionality of momentum or of action. And by coincidence, we are not going to go into deep philosophy. If we divide action or angular momentum on Planck constant, we will get dimensionless quantity. Or there are two types of Planck constant, with and without bar. So if it is with bar, then dividing action on the Planck constant, one is getting radiance, angle. And what is the reason for why angles are needed in trigonometry? Because they serve as argument of trigonometric functions. It's quite a corrupt logic, but what do we do if you have the letter alpha? We put it as an argument of sine alpha. It's not, but it's just associations. So if we design the fraction that has dimension to angle, action divided by Planck constant, we can place it as an argument of some oscillatory function, like sine of a sine. And the original train of thought for people who were designing quantum theory was like, why shouldn't we try just, if you believe that there are some waves, they could put the signs of a sines, we put them the stuff angular momentum divided by something dimensionless. And by some reason, it didn't quite work. I'm not going to go deep into this, but for properties, wavy properties of electrons, the sines and cosines are incomplete and insufficient to give all properties. So one needs to use the concept of complex numbers. Why? Just because it gives reach more. I do not know that, but I have two hypotheses. One, because if one uses the domain of complex numbers, one can get to a larger variety of phenomena, and mathematically there is more freedom. And second one, which is very, how to say, practical, even cynical, if we go through Euler equation, which we are going to do in like 10 minutes, and if we replace sines and cosines to imaginary exponential, right, then we do not need trigonometry. We do not need calculus, or we use them, but in a very much simplified way. So if one replaces trigonometric functions by imaginary exponential, then it is very easy to integrate and differentiate, because derivative of exponential is what? Which function? Exponential itself. Integral of exponential is exponential itself. So through, we will suffer complex numbers on one hand, but on another, we will win a lot by forgetting all this complicated trigonometry and rules of integration. Wherever it's possible, we will just integrate and differentiate exponential and solve equations that look scary, but we will solve them instantly. Make sense? Okay. So I didn't have time to memorize your names and faces because it's a little more difficult in masks. But one of the attendees of the class has minor in math. Okay. And you probably know better how to introduce why complex numbers are needed. Otherwise, what were you doing there? So when ancient Egyptians were measuring bricks for pyramids, they were integer numbers. But when you measure the liquid soup, one is to fractions, right? So if one designs some operation that brings us out of the domain of the certain type of numbers, like integer numbers, then natural when something can be negative, then rational when there are fractions. And if one starts, it started approximately at the time of Descartes, and it was the military application for these catapults and early cannons to predict how far and where the projectile will fall down. And this application needed the quadratic equation, square equation, which is, you see it here, right? Like independent variable squared plus independent variable plus constant equals 0. And by solving this equation, one comes, when I had this equation in mid school, they told us solutions are available only if the discriminant is bigger than 0, right? But solution in the domain of rational numbers is available, but no one forbids us to take negative discriminants if we expand our horizons and design new style of numbers. So solution of this quadratic equation for negative discriminant, the simplest one is x squared plus 1 equals 0, leads to the x equals square root of minus 1. And if we design complex numbers which are like not one-dimensional, like rational, but two-dimensional, then one can always solve this quadratic equation. So square root of minus 1 is imaginary unit, and any complex number is summation of real part and imaginary part, correct? Kennedy, Spencer, and Adam, if please stop me if I'm speaking too quick or something unreasonable. So there is a convenient tradition to plot complex numbers as point on this plane, right? Where x is real part, y is imaginary part. And if we speak on this language, there are two representations. One Cartesian representation through this real and imaginary part, and another is polar representation. One instead of two numbers, x and y, one tells phi and absolute value of z. So angle and distance from origin. And they're quite equivalent. You just need to follow. So I don't care about anything, but I just give you a little heads up so that this information is not a decoration of the course. It is one of the foundation building bricks. So we are, unlike some classes where information is linear and independent, here we are making a building, and we are building the foundation, then first floor, second floor, and without getting this concept, it's not possible to get further. Just a little motivation. So if one, again, the math is done by humans for humans. There is no goal, there is no reason to torture young brains with something boring. All of the things are designed to make calculations which are needed for coefficients most efficient. So if one needs to transfer between polar and rectangular coordinates between this x, y, and distance r and phi, one can compute distance as Pythagorean theorem, x squared, y squared, and the angle can be taken as arc sine of the length to the shoulder, right? And if one knows the distance and angle, one can compute x and y as sine and cosine. Right? I think it's all the same. I don't know much about Euler. I think he was German, he was blind, and he found a job in Russia. And then there is a equation. So if we accept the concept of polar coordinates, right? And if we do not care about distance from origin, if we fix the radius, then a complex number is determined only by the angle, right? And then it is a point on a circle of a given radius. If you set radius equals 1, then it will be circle of radius equals 1. And by changing the angle, we just go across. And on one hand, it will be this sine phi for x, sine phi for y. On the other hand, one can just make a shorthand notation. So that by assuming imaginary argument of the exponential, it will mean that this imaginary exponential is predominantly a complex number with x and y components. To some sense, it's just a shorthand notation for the fact that for the polar coordinates. And surprisingly, it goes along with very nicely with a lot of standard operations defined in calculus. So, any questions, either on the line or in person about the Euler. You approve Euler equation. Let's wait. There could be plenty of answers. Yes, we approve. Yes, we did approve. We don't care. Okay, yeah. Thank you. Where we are. Okay, so if no one objects and everyone approves the Euler equation, then let's make connection to the electronic waves. So it will be very much more comfortable to think that electronic waves have this complex nature, and we, instead of angle, we use action divided by Planck constant as an argument. So it is a mathematical concept that gives introductory vision of what is oscillating in atom and in any electronic system. So when electron is, if you assume circular orbit, if electron is revolving around nuclei, it accumulates action. And this action serves as an angle, as action divided by Planck constant angle argument of the exponential function. And this exponential function oscillates with real and imaginary parts. And this waves is related with, there are conditions imposed on them, and they describe the states of the electron in the atom. If you believe Bohr's model, later on you'll see, and probably you already know that it is very, very rapid approximation, but it's a good starting point. So if you want to forget equations and speak only about convert equations into language of human words, then mechanical motion is associated with accumulation of action. And this action serves as a phase of a wave that describes this motion on a quantum level. So in some sense, quantum theory of all these microscopic objects deals with accumulation of a phase of this wave. And this phase is related to mechanical motion. Okay. I'll skip this slide. It's one of the years there were plenty of time and I needed to fill it. So I'll just briefly point by finger. So there is a side benefit, and it's not in text on quantum, it's my personal benefit. When I was, I think in the either second or third year, I just made a little personal discovery that one can forget all trigonometric functions and rederive them in 1 minute from scratch. So if one practices the Euler equation, and here is an example: exponential of imaginary exponential of alpha, imaginary exponential of beta, imaginary exponential of alpha plus beta. And then one opens, writes down left and right part, either as product or exponential of a sum, and then opens brackets in a sense that one needs to consolidate imaginary and real parts together. And then real part on the left should be equal to real part on the right. Imaginary on the left must be equal to imaginary on the right. And then it immediately provides all this sum, difference, product, sum rules from trigonometry. And this first line is much easier to memorize than one page of equations. Okay. Well, one more property. So if the name of this property is conjugation. Are you familiar with it? Sort of, no? Okay. So, symmetry. If we design two complex numbers with the same distance from the origin and the same real part, but the imaginary part will be opposite. So this red arrows on the screen look quite symmetric. So there is a name for it. So if the one is complex number Z, then the one that is mirror reflected will be Z star. And this Z star is called complex conjugation. So conjugation means that one flips the sign in front of imaginary unit. So where it was x plus I, y, after adding star, it is x minus I, y. And this property will be also very beneficial in things that we are doing. For example, if you practice Euler equation and apply conjugation, then we need to flip sign in front of this imaginary unit. And if you multiply with this complex function with and without conjugation, then we will have the minus in one case and no minus in another one. And exponentials of the opposite arguments cancel each other. So it will be 1. So the imaginary exponential conjugated times imaginary exponential will give 1. And if you provide a lot of comfort when we need to simplify equations, 1 is always one of the simplest things you can get in the answer of some problems. Okay. About 15 minutes. So, I was looking again into text and Wikipedia before coming to you, but I wasn't updating slides. This slide also is worth of $1 million Nobel Prize to Max Born for interpretation of the wave function. So by now, we are still indefinite, and it's not your fault, it's my fault because I reveal part of the picture from strange angles. But after we have complete picture, it will be much more logical and organized. So we do have logical step about the accumulation of action, accumulation of phase that determines oscillation of this complex, something complex oscillating. But what is this something? How does it relate it to real world? What is the nature of this wave? Like we know you are just bringing up the waves of the intensity of electric field for electromagnetic wave, heights of the water on the surface for gravitational this regular waves. What are there are like acoustic waves or compressions of air, but what are the nature of these waves? What are those complex numbers? And the interpretation, well, there are two interpretations, mine and wrong. it's a joke. There are two interpretations, but both of them need to take this oscillator exponential, which is typically referred to as letter psi for wave function. And for interpretation, one needs to take wave function conjugated, psi star times psi. And then by practicing this operation, the same point of space and time, it will become real. On the previous slide, we saw that imaginary exponential star and without star gives 1. And if it is not just, if the radius of complex number is different than 1, it still will be a real number. So by practicing this multiplication of wave function with its own conjugation, we return back from complex domain to the real number domain, right? And this real number domain has two interpretations. One, it is the probability to find quantum particle, electron, in the vicinity of this space x and time t. So wherever this p is bigger, in these areas of space, there is a higher probability to find an electron. But it can be anywhere. But at some positions of space, it has bigger probability. So in this sense, wave function is waves of probability or waves of probability amplitude, because all equations are set up not for the probability density, but for this psi. And in order to get from psi to probability, one needs to do psi star psi. So some people tell that wave function is amplitude of probability. It needs to be taken as for. Second interpretation, which is not accepted as absolute truth, but it is very comfortable for some areas of science, is density of charge. And it is especially needed for computational modeling of molecules and materials. So if instead of probability, one will get crazy for a minute and think there is a 50% of my electron in here. It's a density of electron. It's philosophically wrong. People may throw rotten tomatoes for saying this in public, but it is very, very productive idea in doing some practical calculations on the real molecules. So probability density is correct. You can say it in public. Wave function is gives probability density. No one will object today. 100 years ago, it was highly debatable. And this one you can keep in mind and use whenever one can get benefit. So if one is getting this probability distribution function, and one needs to find, like if one integrates all area under this curve, it will be total probability to find electron somewhere. If one integrates in the infinitesimal range from x to x plus delta x, it will be probability to find in the vicinity. Okay. Let me just quickly check if anyone on the line. What is going on? Any objections? Probability. Again, I agree with this interpretation. I disagree with this interpretation. I don't care about any interpretation. I think the answer is I don't care. Nobody is answering. Okay. Thank you. Let's slowly add rigor to what we're doing. So suppose we do have this wave function, which is amplitude of probability everywhere in space at time equals t. If you are online, please look on the lower right corner, bottom equation, last part. And I will be doing like in Arabic language. I do not know Arabic or Jewish, but I know that they read in the opposite direction from right to left. So this equation needs to be interpreted this way. So if you have wave function at time equals 0, then we can apply our definition of phase accumulation into the front of this function, assuming that for each point in space we know the trajectory, we know the duration of time. So the time goes from 0 to t prime, and then at each point of space by this operation we will get wave function changing its phase. So imaginary exponential is always absolute value of imaginary exponential is always 1. So the total probability, total weight of this function will be not changed. But in one position of space it will accumulate more phase, in another different, so it will change sign and imaginary part, and it will depend on the final time. So by multiplying wave function everywhere at time 0 by this exponential factor, we will get wave function everywhere at time bigger than 0. Make sense? And this gives more certainty, because if you do exponential itself, it's kind of thing in the air. We do not know where the system did start. And now it just gives connection from past to the future. So in each point of time, electron has probability. In each point of space, the electron has probability to exist. And for each of this probable existence of electron, we accumulate more and more phase and change sign of the wave function. And therefore, it starts performing wavy motion. And our goal for part of the course is to design equations that we can solve, or if we cannot solve, we can give a task to a computer to solve them. I will disclose a secret. There are only 5 solvable problems in quantum theory. We want to solve them pen and paper rigorously. I mean, problems related to natural world. All other are just exercises. So it's much more mumbling and theoretical, like theorems, rather than practical solutions. And as we go through the course, I will make this one. So the equation from if you are online or if you are in face-to-face, let me focus your attention on the lower line in the bracket. So previous stuff on the previous slide was telling how to go from the psi at time equals 0 to the psi at t prime bigger than 0. So in some sense, if we master our skills to do this operation, we can propagate distribution of probability from past to the future. If you know past, you can predict the future, which is kind of natural. It was one of the positive side of the Newtonian mechanics. If one knows positions of all points in the mechanical system and their velocities, one can predict where they will be after a certain time. So same is available in quantum theory. So a little bit of notation in the remaining 3 minutes. So past, future, wave function, the imaginary exponential can be called evolution operator. Evolution not in the sense of Charles Darwin, but in the sense of propagating forward, evolving in time. And one often uses the letter U for evolution operator. And for the action, which is integral of Lagrangian, there is a thing that I cannot understand for my whole career. And I saw some papers, but they do not sound convincing for me. If one replaces Lagrangian with Hamiltonian and still computes integral of Hamiltonian from initial to final time, one can use this analog of action as an argument for evolution operator. Do not ask me to prove. I do not know the proof of this as well, but it does work. Okay, so a little bit more rigorous, and in the remaining 2 minutes, we are approaching to the declared goal. So wave function in the past, wave function of the future. Imaginary exponential, here imaginary unit, Planck constant for dimensionalities, integral of Hamiltonian, which is total energy, over time, from initial time to final time. So through this evolution operator in yellow, we can propagate from the past to the future. And I don't know if I have this better. Yes, I do. Timeline can be chopped onto infinitesimal increments. And the evolution can be chopped onto infinitesimal evolutions. So instead of a long evolution for the whole time period, we can do microscopic or infinitesimal evolution. And instead of integral, if this time interval is short, we just do product. Value of total energy times delta T. Multiply exponential, value of total energy times delta T. Blah, blah, blah. So by making this infinitesimal multiplication of the past to the future, we go more and more. For example, here I'm looking on the second line of equations with the curly bracket. So wave function in the past multiplied by this imaginary exponential of the first time interval. And now I'm going to the next line. It gives wave function at time t1 equals delta t1. If we apply one more infinitesimal exponential, I'm going to the next curly bracket. We are getting wave function at time t2 equals delta t1, delta t2. So one can incrementally propagate wave function through the timeline. Okay. I think it is enough for today. Thank you for participating in the discussion. Everyone is free to leave. I will stay here to check and answer if there are any online questions, but meeting is done.
Thank you.
Sure. No lab tonight. No lab yet. Team, Kennedy, any questions or comments? More questions one, more questions two, more questions three. Okay, I'm going to disconnect, but if you come with more with some questions, please email them to me.